Howdy and welcome back. So in this, I guess, example, we're going to implement our first class whose objects derived from this class blueprint will be the proud owners of at least one dynamically allocated object. And in doing so, we'd like to take the RAII approach where we will go ahead and grab that resource during the construction of a vectorint object, and we'll be sure to free it uh, when an object of our vectorint's type is being torn down, so during its destruction. So let's go ahead and get into what this type's going to do, what it's going to be like, what are some of its behaviors, what will it store, etc. So let's design and implement vectorint to be a simplified version of the standard library vector that we're already familiar with. So if we kind of think about how this operates, it's kind of provides us the capability to store some arbitrary number of integers and something that kind of resembles an array, however, with a lot more functionality than what a primitive array in C++ would afford us with. For instance, there's different things we can ask objects of this type to do, such as pushing back something onto the end of its dynamically allocated array, also asking its size, its capacity, or for a specific element residing within its collection of integer objects. So if we want to store a collection of, say integer objects, we're going to need some sort of array to do this. If we want that array to essentially be able to scale at runtime, we're going to have to place that array on the free store. So for vectorint, one of the data members that we're going to definitely need is going to be a pointer to a dynamically allocated array of integer objects that resides in the free store. Furthermore, since primitive arrays, and that's what that pointer is going to be pointing to, do not know their own size, our objects of vectorint type are also going to need to store the number of objects currently residing in that array, as well as the maximum number of objects that we could put into the current array that pointer is pointing to. And obviously, once the size meets capacity, we'd have to go ahead and do some sort of resize operation so that we could go ahead and scale this up with some arbitrary number of integer objects that we will store in our overly simplified collection of them. So in addition to these data members, we'll obviously also need to provide some sort of interface to interact with them, as well as any sort of object of a vectorint type. So here's what I came up with. Again, this is going to be a very, very simplified and naive version of the standard library vector int that you're already familiar with. Objects of this type are going to have three data members, as previously described, a pointer to an integer object, which will store the base address of some sort of dynamically allocated array, the size, so the number of objects currently residing within that array, as well as the capacity of that dynamically allocated array. We will have a single parameterized constructor, which will take the size of our vector event, like that we would like to go ahead and allocate for, as well as an initial value so that we can set each value within that array with some sort of well-defined starting value. We'll also have a destructor, and then we'll have a couple of additional functions. We'll have size, which will return the value stored within the size data member, capacity, which will do the same for capacity. We've overloaded the subscript operator to return both a reference to an object within array, as well as a constant reference to an object within array. For the case of, say, when we pass objects of this type by constant reference to a function, well, only those functions who are denoted as const are able to be invoked on that constant object. So this will provide two ways of allowing us to go ahead and access the individual members stored within an array. In one case, we have a read only. So that is the one returning the constant reference to an integer object. The other one would allow us to actually read and write to that particular object residing within the array. Finally, the The fun one here will be pushback. It will take a singular integer value that we'd like to go ahead and tag on to the end of our vector here. And this is going to simply return a self-reference so that we're able to chain calls of pushback together. So as previously noted, our goal here is going to be to implement vectorint as a container capable of holding an arbitrary number of integer values or integer objects. As elements, so integer objects are added, we would definitely like to have the ability to grow our array as necessary to hold some number of them, memory permitting. So in the case of, let's just say we declare vi, a vector of integer object, whose, if we go ahead and look at the parameterized constructor, whose initial size will be one element initialized with 0. We can see that we go ahead and we will be, if we were to print out the composition of that vector, we have a size of 1, a capacity of 2, and we'll get into how the capacity was determined when we define this constructor. But just for, now I'm for the purposes now, notice that there's one open spot, one used spot, the total of 2 spots available. The base address to that array is going to be shown here in green. Notice that when we push back the integer value of 2 to our array, we can see that size increases by 1 and that the integer value of 2 is added to the end of our dynamically allocated array. Notice that the base address to that dynamically allocated array, which will be stored in the array data member, has not changed. Now let's say that we wanted to go ahead and push back an additional value and grow this, vector a little bit. Well, right now size is at capacity, so there's no room to add 11 to it. So somehow in our pushback behavior, we're going to have to check for this condition and somehow go ahead and resize the array pointed to by array so that we can make room for this new integer value. In this case, you can see here that the result of this function did allow us to successfully push the value of 11 onto our array. We can see that the size has increased by 1, 2, 3. And the interesting thing here is we have a new capacity of 4. So the capacity doubled what the previous array's capacity did. And to confirm that this is indeed a brand new array, we can see here that, and this is the base address to the array, so this would be what's stored in the array data member, has changed from the previous call to pushback. So if you think back to how this would have had to happen, we went through an array resizing process in one of the introductions to dynamic memory lessons, where we said, well, in this case, we have to allocate a new array, copy over the data from the old array or the outgoing array. Once that data is copied over, we can deallocate memory for the outgoing array and go ahead and hook the pointer up to the new array. So before this, array was pointing to that address. After we attempted the pushback of 11, it was now pointing to this new dynamically allocated array. And the previous one would have had its memory deallocated. So our vector of int is going to control access to a dynamically allocated array, so to a resource. The question becomes, where should we acquire this dynamically allocated array, and where should we release this dynamically allocated array? And this is really much just hoping that you're making the connection with the RAII stuff. Where we're going to acquire it's going to be in the constructor. Where it will finally be released is going to be within the destructor. And we'll see here that we'll eventually define a resize function where some intermediary arrays will be swapped in and out of to what array points. So I have a class UML diagram here on the right in yellow. And I went ahead and just translated this into a C++ class definition here. So we can see that vector of int is going to have a couple of public behaviors, just as we specified within the UML diagram. I will go ahead and acknowledge that I am going to add some additional private helper functions to support the implementation of some of those behaviors. They were not shown within the initial diagram, but they wouldn't be accessible to us outside the class anyhow. So anyways, we have this constructor destructor, a couple of getters for size, both appropriately labeled const. We have two versions of our overloaded subscript operator. I think I realized I had said at back then, but we're going to go ahead and overload the subscript operator for the sole purpose that I didn't want to have any sort of range checking. The at version in the STL does, the subscripting doesn't, and that's what we're going to go ahead and show here. We have the pushback behavior, and then the private data members declare they after. Array is going to be the pointer to that dynamically allocated object. Size is going to be, again, the number of slots that array has who are occupied, and capacity would be the total number of slots available within that array.